When we encounter polynomials with degrees higher than 2, simple factoring methods often fail. How do we break down a cubic or quartic expression into its linear components? Today we will master the process using graphical analysis and synthetic division. Factoring is essential for finding the roots of an equation. These roots represent the exact points where the graph of the polynomial crosses the horizontal x-axis. Understanding these intersections allows us to visualize the behavior of complex functions. Before we divide, we need a starting point. The rational root theorem provides a list of potential candidates. By dividing the factors of the constant term by the factors of the leading coefficient, we narrow our search significantly. A quick look at a graph can save time. If the curve appears to cross at an integer value like 1, we can test that value first. If the function value at that point is 0, we have found a factor. Synthetic division is a shorthand method for polynomial division. We write the root we are testing on the outside and the coefficients of our polynomial in a horizontal line on the inside, ensuring we include zeros for any missing terms. We bring down the first coefficient, multiply it by our root, and place the result under the second coefficient. Adding these values gives us a new number. We repeat this cycle across the entire row until we reach the end. The most important part is the final number. If the remainder is 0, the value we tested is a true root, and the corresponding binomial is a factor. If it is not 0, we must try a different candidate from our list. The numbers remaining in the bottom row represent the coefficients of the depressed polynomial. Because we divided by a linear term, the degree of our polynomial has dropped by 1, making it much easier to solve. Let's try x cubed minus 4x squared plus x plus 6. Testing -1 through synthetic division gives us a remainder of 0. We are left with a quadratic expression, which we can now factor using standard methods. Now we focus on the quadratic part. We look for two numbers that multiply to 6 and add to -5. Those numbers are -2 and -3, giving us our final set of factors. By combining our first successful root with the factored quadratic, we achieve the complete factorization. The polynomial is now fully decomposed into 3 linear factors, revealing all 3 roots of the original cubic equation. For a 4th-degree polynomial, the process is the same, but repeated. We find one root to reduce it to a cubic, then find a second root to reduce it to a quadratic. Persistence is key when dealing with higher degrees. A common mistake is forgetting placeholders. If a polynomial skips a power, like x cubed minus 8, you must include zeros for the x squared and x terms in your synthetic division setup to maintain place value. Sometimes a factor appears more than once. Graphically, this looks like a bounce on the x-axis rather than a crossing. This is called multiplicity, and synthetic division will work for that root multiple times. To summarize, start by listing possible rational roots, use a graph to pick the best candidate, perform synthetic division to reduce the degree, and finish by factoring the remaining quadratic expression. Try this one yourself. Use synthetic division to test if x equals 1 is a root for x cubed minus 7x plus 6. Remember to use a 0 placeholder for the missing x squared term. Dividing by x minus 1 leaves us with x squared plus x minus 6. Factoring that quadratic gives us x plus 3 and x minus 2. Great job mastering higher degree polynomials. Generated by Vision Solve AI.